Section 9C, solving quadratic equations by completing the square. Now, in the last section, we learned how to solve by using by factoring. But not all quadratic equations can be factored. In fact, the majority of quadratic equations cannot be factored. So we need to know some other method of solving these types of problems. For our first example, I'm going to use x squared plus 6x minus 1 equal to 0. And I'm going to solve this using our new method called completing the square. You notice if I try to do this by factoring, using our x method, we need factors of 1 that subtract to equal 6. Well, the only factors of 1 is 1 and 1. And when I subtract them, I get 0. I don't get 6. So I know this cannot be solved by factoring. So this is a method that I would need to use. So one of the ways to solve this is using complete the square. There are 3 steps to solving any complete the square problem. Let's look at those steps now. Step 1, we need to rearrange the equation so that the constant term is on one side of the equation by itself. So that means all the terms that have an x need to be on one side and all the terms without an x on the other side of the equation. We're going to choose sides based on our x squared term because, again, we want our x squared term to be positive. Step 2, we're going to add a constant to both sides of the equation so that we can complete a perfect square. So remember in our previous section we learned perfect square factorization, which stated that if we have x squared plus 2 times a times x plus x squared, that would factor down to x plus a quantity squared. And likewise, if we had an x squared minus a 2 times ax plus a squared, that would factorize to an x minus a quantity squared. And so that's what we're going to do. We're going to figure out how to make our equation a perfect square. And then we're going to solve the quadratic equation using inverse order of operations. So for example 1, I need to add 1 to each side so that I have that constant on the side by itself. So I end up with x squared plus 6x is equal to a positive 1. So I have my x terms on one side and my 1 on the other side. Now I'm going to look at the left-hand side, the side with the x's, and I'm going to rewrite it so it looks like a perfect square. And the key with that is notice I have to have the first term needs to be a perfect square, the last term needs to be a perfect square, but the middle term needs to be double the product. So I need to take a 2 out. So I need to rewrite 6x so it's 2 times some number times x. Well, 2 times 3x equals 6. And I know my last term in a perfect square needs to be plus whatever that a term is squared. So I need to take 3 and square it and add it to my term. So I need to add plus 9. 3 squared is 9. But whatever I add to one side of the equation, I must add to the other side of the equation so I don't change the problem any. Now I'm going to take that x squared plus 2 times 3x plus 3 squared, and I'm going to rewrite it as my factored form, which would be x plus 3 quantity squared. Now I'm going to take the 1 plus the 9 and add it together to equal 10. Now I just solve this equation as we did in section A. Get the x by itself by using inverse order of operations. So I start by taking the square root of each side. So I get x plus 3 is equal to plus or minus the square root of 10. X is equal to negative 3 plus or minus the square root of 10. Now always remember to check your radical and see if it simplifies. In this case, the square root of 10 is already in simplified form. Okay, let's look at another quadratic equation. First, I want to check and see if I can do this by using our factoring method. So factors are 4 and 1 and 4 and 2 and 2, but neither one of those subtract to equal 4. So I can't use factoring to solve this. So let's try complete the square. So let's get the constant by itself by adding 4 to each side. Now I need to set this up so the left-hand side is a perfect square. So first I need to rewrite the middle term as 2 times some number times x. So 4x is the same as 2 times 2x. And then I need to add the 2 squared. And then when I add to one side, I need to add to the other side. So that means I have x plus 2 quantity squared is equal to 8. Now I just solve this equation by using our inverse order of operations. First thing we're going to do is we need to take the square root of each side. So I get 8 plus 2 is equal to plus or minus square root of 8. But remember, plus or minus square root of 8 is the same simplified down as 2 the square root of 2. Because I can rewrite square root of 8 as square root of 4 times the square root of 2, which is 2 times the square root of 2. And then I'm going to subtract 2 to each side. So my solution is x is equal to -2 plus or minus 2, the square root of 2. Let's try this again in example 3. So I need to get the constant term on the side by itself. Set it up so I can do complete the square. So 1 squared is 1, so I need to add 1 to each side. Now notice I have a quantity squared equal to a negative number where it's impossible to do. So we know that there is no solution to this problem. In fact, there's no real solution. We're learning at the very end of this section that there are some solutions to this problem. They're just complex. Let's look at example 4. Here, this example is different because our x squared term has a coefficient of a number greater than 1 or different than 1. So we have a coefficient of 2. This requires us to do a little extra work when we're doing the complete the square, but it's not hard. We can do it. But I already noticed this is already set up for step 1. I have all my x terms on one side by itself, but then I have the constant on the other side by itself. And I need to rewrite 2x squared plus 6x so it fits that perfect squared factorization that we know, that formula. But notice that formula has the x squared by itself. It has no number in front of it. It has a coefficient of 1. So that means I need to get rid of this 2 in front of my x squared. It's really easy. You just factor it out. So I'm going to factor out the 2. So I'm going to rewrite this as 2 times parentheses x squared plus 3x close parentheses equals to 1. And then we'll solve it like we did the other problems. That means that what's in parentheses, the x squared plus 3x, is what we need to write in our perfect square trinomial method, perfect square factorization. So I'm going to take my x squared, and I need to write 3x as 2 times some number. Well, 2 times 3 halves is equal to 3x. So I'm going to rewrite that as 3 halves. Then I need to make sure I have that middle term. So I need to take that 3 halves, square it, and add that to the polynomial. But here's where most people make the mistake. Notice I'm not just adding 9/4 to this equation. I'm adding 9/4 times 2 to the left-hand side of the equation. So that means I must add 9/4 times 2 to the right-hand side. Do not forget to multiply by 2 when you do this. So using our perfect square trinomial, I know that breaks down. Combining our like terms. And now all left to do is to solve this equation using our inverse order of operations. So I'm going to start by dividing each side by 2 because remember, inverse order of operations, we got to do multiplication division before we do the square root, the exponent form. Now that I've divided each side by 2, I can now take the square root of each side, and always remember to simplify this radical as we've learned in previous sections. So that becomes the square root of 11 divided by square root of 4, or the plus or minus square root of 11 over 2. And finally, I need to get the x by itself by subtracting 3 halves from each side. So my answer is x is equal to negative 3 halves plus or minus the square root of 11 over 2. All right, let's try example 5, where again we have a number in front of the x squared term. So first, let's get all the x's on the side by itself by subtracting 2 to each side. Then we need to factor out a 3 from our x side of the equation. So we get 3 parentheses x squared minus 2x close parentheses equals negative 2. Rewrite the x squared minus 2x so that we have a perfect square trinomial set up. And so I need to add 1 squared to the left-hand side. But remember, to the right-hand side, I got to add 1 times 3, the number outside the parentheses. So this becomes 1 minus x quantity squared. And then simplifying that down, we have 3 times x minus 1 quantity squared is equal to 1. Now we're going to solve this using our inverse order of operations. So we need to divide each side by 3. So that's x minus 1 quantity squared is equal to 1/3. Take the square root of each side, and I get plus or minus square root of 1/3. Simplify the square root of 1/3 using processes learned previously in the year, and we find that x minus 1 is equal to plus or minus the square root of 3 over 3. Then we're going to add 1 to each side for a final solution to this quadratic equation. All right, in example 6, at first glance, this does not look like a quadratic equation. It looks like an algebraic fraction from our last unit. Well, it is, but it's also a quadratic equation. Now remember, one way that we learn to solve equations like this is to multiply the left-hand side and the right-hand side by our least common denominator. In this case, our least common denominator is x. So multiplying the left-hand side by x, we get x squared plus 8. And multiplying the right-hand side, we get negative 5x. Now let's write this as our quadratic, so that's x squared plus 5x plus 8 equals 0. Now to solve this using the complete the square method, I need to get the constant on the side by itself. So I'm going to subtract 8 from each side. So I have x squared plus 5x equals negative 8. Now we're going to set this up for the quadratic method by factoring out a 2 from the middle term, so I can rewrite 5x as 2 times 5 halves x, and 5 halves squared is 25 fourths. And when I add to the left-hand side, I need to add to the right-hand side, so I need to add 25 fourths to negative 8. The left-hand side becomes a perfect squared, and that perfect squared is simply x plus 5 halves quantity squared equal to, now we need to figure out what negative 8 is over 4, which is negative 32 fourths. And combining like terms here, we end up that this square term is equal to a negative number, negative 7 fourths. But remember, a square cannot equal a negative number and be a real solution. So there's no real solution to this problem. Our answer will be complex solutions. But for now, just write no real solution. We'll learn in our last section how to deal with this. You know how to solve equations by completing the square.